Oui, enfin, si jamais ça me donne. Ah oui, I.
The thing is that now that we have really depending on when we have to rewrite the code, the location of the number.
Okay. So let's start the demo. I'm Samuel Garcia. So I'm. Yeah. No. No, it's okay. Let's keep this. It's under control. So I am a French engineer. I'm super happy to be here to make the demo. It's okay. Let's try. Now, I'm happy to present and to make a demo on SpikeInterface. So my English level and grammar is really bad, and I'm sorry for this. But normally the Python code we did is quite clear. So it compensates a bit the low level of my English grammar. But I get two good teachers yesterday for the dinner, so I improve a bit. So normally you get feedback. Okay, pas bon du tout. Turn off. Okay, 1, 2. Okay. Normally you receive an email. You are supposed to go. Feedback, no? Ah oui, okay. So you have a link, and you are supposed to be in this page, which is a GitHub repo. Maybe you already know what a GitHub repo is. You're supposed to download this or to make a Git clone. And we prepare a lot of notebooks for you, and I represent quickly 2 notebooks. So you need to download this on your computer for the afternoon. The 2 first notebook, you don't have to execute them. It's just a demo, just to listen. When the notebook is on your computer, maybe you already know it perfectly. You have to start the Jupyter machine to run your notebook, which is a system. So for this, you need to go on a console to activate your environment. If you use Conda to make Conda, activate, SI tutorial, stuff like this. You have to do Jupyter Lab, something like this. And this will start. I just tell this for beginners. And you do Jupyter Lab. Oh, on voit rien du tout. And when you do Jupyter Lab, it's starting from Jupyter in your browser. And from here, you can open some files. And here you have a Jupyter notebook ready to be run. So it's one way. The other way, maybe it's for beginners, but I can see when you have your file here, you can open the folder with Visual Studio. And if you have the Jupyter plugin, you should be able to double click on any IPyNB file, which is a Jupyter notebook, and should be able to run, save by itself the notebook. So I will use the browser version, but it's the same. I will try to make it full screen. Okay. And just before starting a real demo, I will run this on a simulated dataset, not a fake, which is a fake dataset, but we say simulated, just to get the insight what SPI sorting is, and maybe you already know it, but it's some kind of beginners and on SPI sorting. And I will not give too much detail on the SpikeInterface. So I will run some cells by pressing this, or you have a shortcut with Control-Enter. So I'm loading the modules. And what we have in SpikeInterface is some kind of layer that generates some data. So in short, the data I will read will be a recording and a sorting. In fact, 2 recording, 1 drifting, 1 not, and a sorting object. So I'm not reading from file. It's a generator of file. Okay. So here what I did is a really simple case, the good old days with a tetrad stuff. And we have many parameters to control the drift and everything. And here I will put only 5 units Okay, so simple case, 4 electrodes and 5 units. Okay, so once you have your object, something which is cool in SpikeInterface is that we have many ways. Ah, ça va être compliqué avec la barre. Hein. Boom. To display the traces. One is to use, for instance, the if you viewer stuff, and when you have this, it's easy to go to traces. And if you know what spike sorting is directly, you see that we have quite good units, and you directly see that the units is on several electrodes at the same time. So you clearly see some fire here of the units. You can zoom in and out, but and you clearly see that you have small cells and big cells firing on many channels. Okay, and we want to catch these cells. So it's the goal of spike sorting. So what we did with Pierre to teach this this stuff is that we develop a simple spike sorter, some kind of toy spike sorter that include the 2 first steps of what Pierre presented, which is catch the waveform, project in a subspace like PCA, and then run any algorithm you want. In that case, we will use HDB scan, just to see what happened that I grab so it's what I will do now. I will do run sorter with the simple stuff. So internally, it detects some peaks, it puts this in a shared memory buffer, and it runs it, and it's super fast, okay, because it's only 4 channels. So now I have this object, which is sorting something, and it tells me I have 7 units. First, you see the first problem. I have more units detected than the one I'm supposed to have. And maybe there are small units I could not see. So just to have the insight, I could open back the features, which is, let's say, 5 or maybe 3 features per channel. So I can open this file. And you can see that I have many spikes, 3 features by channel. I can flatten this, which is my feature 12 space. And maybe I can use a map prediction story to have an insight or what are the good clusters. So for this case, I use a UMAP, but you have at least stuff to display this. I'm pretty sure you already know this. This step is quite slow. It's not to compute the clustering, it's just to visualize in 2D the clustering. And here you see that normally you have a good clustering because UMAP can split this. You have strange stuff like this, but normally we should have pretty easy clustering. And if you go in detail, what we can do in SpikeInterface is to run an analyzer to mix the recording and the sorting discovered by the simple sorter. We mix them together, and we run many stuff in between to extract waveform, compute the PCA again, not internally by the sorter, but new PCA, compute some SNR. And with this object of the analyzer, the very first stuff we could do is to display it. And for self-promoting stuff, I will use the SpikeInterface GUI, which is not working. It's supposed to open a window. But for no, it's here. So here we have a GUI. I will not give too much detail on the GUI, but here you have the probe representation. You have several views for the GUI. Ah, ça marche pas bien. It's a demo. Attends. And on one of the view, c'est la barre qui. On one of the view, you can see the waveforms. And when you click or double click on a cell detected, and you have the position estimated on the cell, you can check any waveforms. And very quickly, you can see that some of these cells are the same. Okay, so the clustering split them, but you can see when you see this that it should be the same. Okay, so the clustering step is complicated, and maybe just to give you an insight, in that case, it's because it detects some kind of shifted version. So the sampling itself can act on the clustering step. So here you clearly see that these 2 steps. So at some point, I want my cluster or my sorting algorithm to remove this, or maybe I will need to myself group these two clusters to get something. You can see here also that you can select units by SNR, and the biggest one maybe are the better. You have also some other view. I will not show the cross hologram and so. Some important view also is to see that here you have the noise estimation in gray, okay, with several SNR MED. So you want 1, 2, 3, 5, and you expect that big cells with high amplitude distribution, this is the amplitude of distribution of the peak, should be more easy to catch than the small one that could overlap the noise. So it's an important concept for the what following, that the amplitude of my cell could overlap the noise, and I expect my sorting algorithm to be able to remove this kind of low noise overlap. And if not, maybe I will want to estimate this. Okay, so it's some key features. In our case, because we have the ground truth, we can also make the analyzer on the ground truth itself, display it. J'aurais pas dû mettre en plein écran. Display it, and here it's the analyzer, but with the true recording. And if you explore the true cells, clearly, some cells, some units are in the noise. So they should be more complicated to discover. So in short, I have, in that case, 2 super easy, 2 super complicated, and 1 in between. And in our case, we can use SpikeInterface to challenge our sorter, the simple sorter, which is a toy. We can compute the agreement between the ground truth and this toy sorter, and we clearly see that our sorter is making some mistake. So this is the ground truth, this is what the sorter discovered, and this is the agreement. So clearly this cell is almost perfectly discovered. This one not, because it's split with the 2 ones, so it's a big one, maybe it's the shifted version, okay? This one is split in 2, and this one is poorly discovered. Maybe it's between the noise and the not noise. And also this one is not discovered at all, okay? So this is with a simple sorter, but it's what we were doing, let's say, 15 years ago. It's what more or less the workflow. And here, it's a static toy simulation. At the same time, I made the same recording, but with a really small drift. So, first, before this, we can use some metrics to clean this sorter. So we will give more detail later, but I can compute some metrics. I can filter units given this metric quality to reduce and remove some units. And I can make a new analyzer with it, plot it again, and then it's the SPI sorting story. So you plot something, you have some rules with the quality, you open back, and it's the main idea. Okay, and then at the end, when you make the curation, in our case, it's easy to. J'aurais dû prendre une souris. You can. Attends, I lost the page. You can plot the ground truth of the curated one, but even the curated, because we are not making merges, it's not perfect. And now, just as a toy example, but just to get the feeling of this, I am running on the same data set with just a small motion. And you have to have in mind that because it's not a dense probe, the motion information is impossible to recover. You need some kind of dense probe to estimate the motion vector. For tetrod, it's impossible. We don't have any clue to how to reconstruct. So here, it's just to see what could happen. So you can also open this. You clearly see that if you go on the amplitude representation of any cells, for instance, I double click here, that the amplitude is going up and down because the unit soma is going out and nearby any channel. Okay, so it's the story. And if you do this until the end, but I go directly to the conclusion. Attends, no. I go directly to I do some computation. but you will see clearly that if you plot the agreement matrix in that case against the ground truth, the result is catastrophic with this sorter. Maybe some sorter could do better. So here, in that case, I have only 2 cells discovered by the same sorter. And you see that clearly we are doing some over merges, which is a complicated case. Normally, good sorter in that case are doing over splitting. Maybe you could have a chance to take the pieces of different units and put them together to have a perfect unit. In that case, it's more complicated because the sorter itself failed the clustering steps by merging everything together in 2 big units, even if we have 5. Okay, so it was just a quick demo to get the main feeling of the spike sorting. So we will check the other notebook, which is now a more legacy tutorial with a real data set. How many minutes do I have to? On doit finir. Bon, I will do. If it's too long, you stop me. So for this, we will use a data set recording with a zebra finch. So this is this bird with a Cambridge Neurotech probe. So not anyone is using NeuroPixel. You can use other probe. And we'll use this probe. And they recorded this with the traditional OpenIFEs with a USB board. So we can read this data set. And this is nicely provided by the Arthur Lebois in Bordeaux for the demo. Okay, so you can download the data set. Then in Python, in the Python world, you need to import explicitly your package. There's a big fight in SpikeInterface how to import SpikeInterface, to import each module separately or everything in once. I prefer this line, which is everything in one, that you do what you want. You can check the version number, which is important because the change of the version could change your results. So it's some kind of, if you want to do reproducible stuff, you need the feeling of which version of what software you are using. And it's not one software, it's the full stack of the software, which is important. And then in Python, we will define, and it will be important for you to define this. Where is my data? So in that case, my data is on my computer. So I use an absolute local path. And then you can do with Python related stuff. And with one line of code, I'm able to read OpenIFEs folder. I don't remember the size, maybe it's a few gigabytes, but you realize that I'm able to read this file instantaneously. The why is because we are making lazy reading. We are not reading totally the data set. We are reading only the headers, how much channel, what's the sampling frequency. So when I plot this object, it tells me that it's an OpenIFEs recording extractor, so the abstraction Alessio was mentioning, and you have some information, and you can also use the HTML display of Jupyter to have more and a cooler version of the display with the channel IDs, some annotation, and the channel properties. And this was recently added by Ramon. Merci. And of course, because you have other formats, the reading the data is simple. If you have NWB, you do read NWB. If you have SpikeGLX, you do read SpikeGLX. If you have Plexon, you do read Plexon. So we support many formats. Okay. And now, if you want really to access the data, so what you need to do, and it's on demand, you tell the reader, so this recording object, give me the traces. And this is the lazy on-demand stuff. So give me 1 second of data, given this sampling rate, and it gives you some kind of matrices, which is timed by channel. In our case, we have 74 channels, okay, which is standard stuff for OpenIFEs. You have 64 for the probe and 8 auxiliary channels, okay, in mind. So we need at some point to separate this 8 channel, which is the behavior, and this 64 channel. Okay, and this is why we did the probe interface side package, which is to handle the probe. So I will go quite quickly to this, but the idea is we have a collection of probe, and lucky us, we have the probe, all the probe from Cambridge Neurotech. So in one line of code, I can download this probe on my computer, which I have done now. And when I do print the probe, it gives me some information of the probe. And lucky us, we implemented several pathways. So the way we are making the wiring, this complex wiring, which is really tedious and can be dangerous if you do the reverse way. So we implemented a few of them. We've tried triple blind test to be sure that we are not making mistakes. So normally this one are more or less guaranteed by us, but we hope there's no mistake in this. In that case, it was recording with the Cambridge Neurotech mini-amp that have also a special mapping, which is not the same as Intel, it's a special mapping. So we use this line to make the mapping. And then we have internal function to make to plot the probe. And here you see, but Zach will give more detail. You see that the name of the probe, which is ID given by the manufacturer, is different for the name of the wire. This is the number of the wire. And if you continue, so this probe, we will attach it to our recording with one line of code, said probe. And then we have a new recording object. This was my recording object with a 72 channel. If I set the probe, I get a new recording object. And this new recording object has less channel. This is because our probe description is able to say, oh, this is my channel in this order. And then you get a new abstraction of the new recording for that describe my recording without the 8 channel I don't want for the sorting. Okay. When it's done, because I attached the recording and the probe, now I can see the channel name from OpenIFES. Okay, the channel ID. So I can make the link between the name of the manufacturer and the name of the recorder. I can group them directly. And normally there's no mistake, but you should check. And now one way of this is immediately what you can do is to use the IPy widget layer for plotting we have to inspect the traces. And because we have many traces, we are using this kind of map stuff, which is a bit weird because at that stage, it's not yet filtered. So maybe we can see less channel and we can make this you can see that clearly we have some spike somewhere and we want to detect them. Okay, I will go briefly in the following stuff. We can also attach to any object of a SpikeInterface some properties and annotation and metadata, which is cool when you want to track your data. You can give name or situation or in that case, and it's important. We already have properties attached to our recording, which are the channel names, but also the gain, the internal gains with the numerical representation and the real data in microvolts. Okay, you can attach more properties using this function. Okay, and you can see that when you do this, you have more and more property. For instance, here I use a fake property, which is this is good or not. You can attach this to all the channel, or some channel can be missing. This is it. Okay, so it can be done at the channel level. So you need to make a property by channel, or at the global level, which we call an annotation. Okay, which is some kind of a scalar property for the entire recording. In that case, I give the annotation description on this recording and annotate it, and then it's inside the object. Okay, I will keep this annotation. It could be useful if you have many objects to maintain it at the same time and you want to plot some annotation on it. Okay. So now first layer, so we already mentioned a lot, is the pre-processing steps. And we have in SpikeInterface many pre-processing functions. And in Python, it's easy. You put your object in the function, you call the function, and you get the output. So the input is the raw recording, and my output is this filtered recording, my variable name. And if I do this and I print it, it says me, it's not anymore my raw recording, it's a bandpass filter recording. And you see that also for this, it's done immediately. I haven't read the file, filter it, and save it. It's done on the fly. In short, it's a lazy chain of pre-processing. In short, I have not done yet the computation of filtering. It's a description of the filtering that I will apply later, which is cool because with this in mind, you can make a complex chain. For instance, I will apply a common reference that removes the median for any sample. which is the basic denoising story. And even when I do this, so I do the command reference on the filtered stuff, and I get a new recording, which is also lazy. So I am creating some kind of lazy chain of pre-processing. And it will be cool to test if my chain of denoising and pre-processing is good enough very quickly. I don't need to make the computation, reload the traces, and inspect them. Because with this in mind, I can use the same plot we had before, but with a multi-layer stuff. So either you give one recording, but you can give several recordings at the same time. And in that case, you have some kind of multi-layer representation to check any step or any possibility you want to try of your recording. And this is super convenient because this is lazy. So here you see 1 second or 100 milliseconds of your data, but you can jump to the end of your data set, and on the fly, I am getting the traces from the raw binary, applying the channel reduction, making the filtering, and making the command reduction. And this is super lazy. So if you want to revert the command ref and the filtering, or to change the filter boundaries or any pre-processing, you can try several stuff and use this kind of widget to check them on the fly, okay? And you can use also the line mode to have a better representation. You can also plot them together on the same. I go back to this. You can select manually some channel. When you do this, you clearly see, and it was mentioned yesterday several times. Yeah.
Where is the chain of those operations held?
It's internally handled by the object. I don't show you now, but internally we have a dictionary which tells my father is this one, and internally is this one there. And you understand, and at the end, it's a reader, so it's an extractor of the formats.
Okay, yeah.
So it's simple. Internally, at the end, it's quite simple. And of course, when you do get traces, you do get traces from the parents, you apply the stuff, we do the same with the parents, etc. It's a simple chain. But the important stuff is the concept.
Yeah.
So here you clearly see that on the border, we have bad channel. We mentioned a lot of time this morning and yesterday again and again. You can also use IFI viewers, which is another back end. So for any plotting function, you have several layers of plotting. One is the matplotlib, so it's a flat representation in the notebook. We have the IPy widget, which is a dynamic representation in the notebook. We have a Qt stuff that I did, which is quite fast for display. Unfortunately, it works only on your local computer, so you cannot make remote display. But if your data is local, you could use it. It's quite fast. Okay, I won't go too much in detail. And now I will run a layer function we have, which is taken from the IBL lib, which is detect by channel. So they introduced some method. I think we improved maybe a bit, some of them. And we have this function. It gives you which are the bad channel, and it gives you also a vector to describe the channel. So dead or good or noise or stuff like this. And so if you take this idea, vector IDs of bad channel, we have on the recording, we can apply the remove bad channel, and then we have a new channel reduction object, or we call it channel size recording, we don't care. And now the trick is, and it was mentioned by Olivier, is that it's bad to apply a median subtraction on all the channel if you have bad channel. The best is, because it's lazy, I will have a recording filtered good after the bad channel removing, and I redo a new command reference only on this. It's important. So have this in mind. Yeah, when you do pre-processing, because it's flexible, you can do what you want with SpikeInterface, but it's good to make it in the good way. The good way is to filter, detect bad channel, remove the bad channel, and then apply the command ref. So it's a short detail, but important. And then you can plot it, and you see that it's not perfect. We will not explore all the parameters of bad channel. We have somewhere some option to play with the threshold, and we should play with the threshold maybe to remove these two ones. Okay, and voila. And normally, if you go in this, so we don't have many Spike on this. It's a hard case in this because it's quite silent. And thirdly, we have many spike firing when the bird is singing. So it's a complicated case for the spike sorting. You will see this just after. So for the demo, I will reduce, I don't remember the length of this, but I will reduce this to 5 minutes to be fast enough to make the demo. So we have also some function to manipulate the timing. And Ramon will present this afternoon. So I can reduce my data set to make some check. I can concatenate some pieces of data to make some kind of chicken test recording. We have all the machinery to do this. Okay. And because this object is lazy, so until now, so this recording shorten did not any computation except when I was plotting it. It was doing the computation on the fly on the short pieces I was displaying. Sometimes I need to save my object to get a binary and compact on the disk. It's not necessary, but you could do it. And it's what we will do because KiloSort need as an input a binary file. So we have a function to save it. But to save it, we have, I want it to be fast enough. We have an option to do this in parallel. Okay, so we have some kind of global keyouts to describe how many cores of my machine I want to use to resolve the chain of the pre-computation and save it to a binary file. It's what I will do now. Ah, ça marche pas. So it's super fast. You should be super impressed by the speed of the computation. Bam, it's done. Voila, on a small laptop. Okay, because in my case, I was using all the core of my computer, and it's only 40 channels. It's not so much. Okay. So when my object is saved, I could go on the disk. I won't explore, but it's a folder with a simple binary and a simple JSON object that describe how many channels and what the frequency. So it's super simple to open in any other software. I can reload this object. So now it's a binary folder recording with the same stuff. Normally, you recover all the stuff we put at the beginning on the object. So the quality, the annotation, stuff like this should be propagated on my object. It's important that the information I put on my object are propagated and saved in the file. So this is for the pre-processing modules. Right? Yes, we have a provenance files. No, you don't reload it, but you have a file which is in the folder that describes the provenance when it's possible. Because sometimes you have some stuff which is not trackable. For instance, I could have saved my object into memory representation to make it compact in memory and preloaded. And if I want to save this, I cannot save the provenance because it's a volatile buffer that would disappear, and so I'm not able to load again. So in some situations, it's not possible to reload, but sometimes it is. Okay, so the spike sorting layer, as it was mentioned several times, we are wrapping, so mapping several spike sorter with several technology. So here you see the list, which is available sorter. So everything we implemented in SpikeInterface. But if you want to use a sorter, the sorter needs to be installed on my machine. Okay, so now if I do this on my machine, so it's exploring my machine, I have only KiloSort 4, the simple one, Spiking Circus 3D 2, and 3D 1. So the real one I installed is 3D and this one. The three other one has built-in SpikeInterface. Okay, this one is the one presented by Pierre yesterday. Okay, it's what explained here. Okay, so the first step we will do, we have a unique function to do this, is to run a sorter on my recording. So the recording I saved, okay? For performance reason, I will run it on the save recording. But I could also run my sorter on the non-save, the lazy one, to save this space. If you work on a machine where the disk is slow, maybe it's not a good idea to save it to the disk and read it back because it's slow. Okay, so I will use this function in Jupyter. If you put the question mark, you have many information detail on the function. So the input variable and all the options. And And you can see that you can add sorter parameters. So some options are sorter dependence. In short, we are mapping some option from kilosort 2.5 in this function, but if you run 3D clue, maybe it's other parameters. So we have a function to retrieve which options are available for kilosort 2.5 in that case, and we have all of these. Okay. So the first step I will do is to run kilosort 2.5. In that case, it's a MATLAB-based sorter. So what I will need to do, because it's a MATLAB-based, is to tell SpikeInterface where I install my machine MATLAB. Okay. And I need to have MATLAB on my machine and the MATLAB license and everything. In that case, precisely. Okay. I can define some sorter option with Python dictionary. And then I will run this function, run sorter kilosort 2.5 on this recording and put all the results in this folder. And I want some verbosity. In that case, I will not run it because I don't have MATLAB on this. I did it already in my lab. And what happened in the background is that this function is generating a MATLAB file, opening a MATLAB in the background, running the scripts, getting the results, close MATLAB, and read the result back. It's what we call a wrapper. We generate a code that is run in the background, and then we get the results. It's how SpikeInterface started. And then, in that case, I copy paste from home. I can read the result from this folder. Normally, you get directly the variable here, but here it's a fake code. Not a generated, but a fake code. But I can read the result, and you see that now we have a sorting object. It's really compatible with what Alessio presented. And the sorting object is something which abstracts the output of the sorter. And you have some important stuff, which are the unit IDs, maybe some annotation. For instance, kilosort gives you the, no, it's not here. No, not in the annotation. In the properties, you should have a vector with the label given by kilosort, which tell you it's mu-r, maybe it's a good. So kilosort give you hints, what's the quality of the output. Okay. And if you explore the output folder, importantly, you will see that you will not have only kilosort files, but you have also SpikeInterface files, which is important for provenance and reproducibility. For instance, you can have all the parameters you use to run this case, which is important. You have a log, which is the runtime, basically, and you have also the provenance of the recording. So you can go back to which recording give me this sorting object. Okay, so it's a detail. And so here, for instance, you can print out the parameters used for kilosort, which is kind of a tree of the parameter used. And with this object, also what you have, we have some plotters, and traditionally you can plot the raster plot in time range, and it can be a IPy widget for dynamic exploration, but in that case we use only matplotlib, so it's a fixed image, and that's it. And we can save this object into another format, which is an internal format of SpikeInterface, maybe for other used. Ah, ça marche pas. Pas grave. Ah oui, okay. But it's okay. I don't need. Another important and the main important stuff is that we can run this sorter into a Docker, which was presented by Alessio. The Docker is this kind of virtual machine inside the machine. And in that case, you don't need to install MATLAB and to have the license and anything. And you will see that it's exactly the same code. I don't have kilosort 2 on this machine. The trick is to use Docker image equal true, or Docker or singularity image equal true, or maybe to give the image tag if you want to execute another version of a kilosort 2. We have some tag for different version, and it's only this option to run the sorter. So you run it and you open it, and in that case, you see that you don't have exactly the same number of units than kilosort 2.5. So it's the first warning. First, two sorters with half a version don't give the same result Exactly. You can also run, just for the demo, the KiloSort 4, which is locally installed. So in that case, it's not MATLAB, it's not a Docker, it's directly run with using KiloSort 4 in my environment, which is another case, in the case where the sorter is a Python package. Okay, so I have three sorting objects, and I want to explore these. So for exploring the post-processing and the sorting analyzer, I will use only the one from KiloSort 2.5. So I reload the results and I put my variable in a sorting variable. It's just a trick to make the code more simpler. So it's the one that gives me 169 units. Okay, and what we will see this afternoon in detail is that the very first step is to create what we call a sorting analyzer or an analyzer, which glue a sorting and a recording. When you create it by default, because we have a sparse option here, it takes some time because we need to estimate the sparsity. I will go back on the sparsity story just after. And the analyzer have some extension to compute some stuff. So lazily, I will compute many extensions at once and with few details. For instance, I will take some random spike, compute the waveform, and compute the template and compute the noise level. So I can do this. So I run, and this is the semantic analyzer, compute something with some option. Okay, so some steps are really fast. Some other steps could be slow because you need to load the traces and hold chunk by chunk to extract piece by piece the waveforms to make the computation. But in average, it should be fast enough to get some results. Okay, and it's when you print it, you have a sorting analyzer which tell you how many channels, how many units, how many segments, and he tell me that I have 4 extensions already done. Okay. And this extension handle piece of data. For in case of the in the case of waveform extension, what we do is not for all spikes, but for some random spikes, we extract a snippet, for instance, 5 milliseconds, and we stack them with some kind of sparsity. And if you want the data by this, more or less, we can recover the data for every extension. So in that case, I want for the unit 0 my waveform. And the shape of this waveform is 500 spike, 111 sample, and 8 channel. For the unit 1, it's another number of channel because depending where my unit is on the border, on the middle, maybe the representation have not the same sparsity. Okay, so it's important to have in mind that to analyze the stuff, we cannot afford to extract all the spike on all the channels. We have some kind of sparsity around the maximum on of the templates. Okay, you can also get the templates, which in that, yeah. Yeah, it's by constriction because when I create an analyzer, I choose the recording I want. So in that case, I use the same. Very often you make a preprocessing, you run a sorter, and you create the analyzer on the same preprocessing. It's what anyone do, but it's a mistake. So your question is good. What you should do is maybe to explore your data with another chain to explore. For instance, it's good to see your data without whitening, but use the whitening for the sorting. And by constriction, the recording you give here is not necessarily the one you give to the sorter. Okay, so I was here, so you can recover data for the template. And of course, with the plotting layer, and here in that case, I will use the backend IPy widget. We have some kind of interactive way to explore the template. And this widget have been improved by Alessio recently. Here you have more or less the probe representation. You have some missing channel because it's maybe bad channels. You can see clearly in the representation here. And you have more or less the sparsity of every template. Okay, and you can zoom and you can explore 1 by 1 or 2 by 2 the templates. So now, just a word about the sparsity. We have, so here we let the analyzer make its own sparsity, but it's important sometimes to control the sparsity. So maybe you want to control before the analyzer. we have some function to estimate the sparsity with several methods by radius or by the best n channel or stuff like this. And then you can create explicitly an analyzer with the sparsity you want. Okay, it's a detail, but it's important. And then internally, the sparsity object, I don't need too much detail, is some kind of mapping that tell you for these units, I need this channel to represent the template. It's where the main information is, okay? And it will be used by some of the extension. For instance, the PCA extension will use this sparsity, otherwise it could be too slow. Okay, so any analyzer have a sparsity object attached to it, or not. Sometimes you want a dense representation for tetrod. It's better to use the 4-channel anytime because it's easier to manipulate. Okay, so I will make a short extension tour. It will be done in detail this afternoon, and you will do it by yourself. It will be more intuitive. So we have all these extensions, which are super classic in the Spike sorting community. We compute some quality metrics. We have the amplitude, the correlogram, cross correlogram, the principal components. We have many stuff. You can compute them one by one. You can get the parameters of any extension, because any extension has some parameters before computing. For instance, for the correlogram, you have the bin size, of course. So let's start with the spike amplitude. Okay, so I just do analyzer compute spike amplitude. In that case, I need to go back to the signal. So you have this bar that will show you the progression of the signal traces chunk by chunk recovering to compute this. Okay, you can display the amplitude, which is a good check if you have a drift or not. Okay, you can also check the histogram, which is a good check if you cross the noise or not, if you have an amplitude cutoff like this. You can compute the spike and the unit location with some methods. For instance, the monopolar triangulation is the method developed by Charlie and Julien. And the center of mass is a really trivial method that just take the center of mass. You can do this at the unit level, which take the template, or at the spike level if you want to represent the clue of any spike on the directly mapped on the. And for any extension, very often you have attached to it a plotter. So we have a plot unit location to plot the unit location. So when you click on this one, for instance, you see that this unit is here. So it's not where the unit is. It's an estimation of where's the unit. It's not. If you change the method, maybe you will have another estimation of the unit. So this is for the unit. You have the same to plot the spike location.
Unique location is three-dimensional, right?
Yeah, here we map it only in 2D on the probe.
Couldn't we make a radius circle of RX?
I don't understand.
We have circles for each unit. We could say that the radius of the circle represents its parallel.
Ah, oui, could be done. We are impatient to see the pull requests on this during the
Out
hackathon.
of the spike location, you
Ouais.
might be missing.
No, but for the units.
Yeah.
We have other stuff like the template similarity. And you can plot the similarity, which is to explore the similarity between any template pair. And of course, the diagonal is the perfect similarity. It can help you to detect the merges. You have the correlogram and autocorrelogram, which is globally computed at once in the correlogram extension. So here it's this first figure is the autocorrelogram. So what you are looking for is the clear dip in the middle, which is not the case here. Maybe the sorting is not so good for this data set. And here is the representation of autocorrelogram on the diagonal and cross-correlogram outside the diagonal. So you are looking for stuff that don't have dip on the cross-correlogram because maybe it could be. So it's some kind of tools we will need to use to make merges or split or stuff like this. It will be detailed this afternoon. Et voilà. The principal component, I don't go in the detail. I just compute them for what happened after. We also have metric on the templates themselves. So in short, the peak to valley, the recovering, the width of the spike, and sometimes you can use this to separate two neuron types, excitatory or small neurons, stuff like this. I don't go in detail for this, but we have the machinery and tools to help you to label your neurons, and this is the template metrics function. We have also, it has been mentioned a lot of time, the quality metrics function. So there's two family of quality metrics: the ones which are on the spike trail and the waveforms, and the ones that use the PCA, the representation of the compressed in time. Ouais. Oh, you have sharp eyes. One is giving you back directly the data, and in that case, it's more easy to make the demo. But the data in that case is a data frame, and the other one is giving you the extension object itself.
But they're the same map.
It's the same internally. It's just to, and more or less, this is the old way, the old fashion of doing it, and the dot compute is the new fashion. But
Like the results like average.
alors, the analyzer, I don't go into detail. We have three versions of the analyzer, three backend. One is full memory. One is with a binary representation of everything. One is a ZAR representation. We have in mind maybe to build some remote visualization later, which is not done yet. So internally, everything is handled. Okay. So in that case, this stuff gives me a data frame, which is a table. Every line is a unit, and every column is a matrix. And we will use, or you can use, you have to use this matrix to sort out your which units could be used for your analysis or not. And there's no global rules for this because it really depends on the question. Okay, there's no good rules for this. If you interest in the firing rates, you can keep all of them, or maybe there are many situations all of them could be used, but in some situation you really want single unit representation, right?
How common is the PCA output of the spike sorter? We use kilosort, so it's always there.
No, the idea is what I computed. I went quite quickly. Is we need to recompute PCA. So in short, the PCA, and we have control on how the PCA computed because we have three ways of computing the PCA. We have option on the whitening or not, or stuff like this. Is it the fitting by channel or globally, or is it space and time flattened for the PCA learning? So we have some option of the PCA, and we use internally the PCA for this way. So I don't promote too much the PCA metrics because I don't like it, but it's available if you want to use the PCA representation to make the stuff, right? But it's, voilà. We have the PCA. Here for the demo, and because it's slow, I will not use the PCA metrics. So I have these two family. I will compute only the metrics, which are the non-PCA metrics, but you could compute all of them, okay? In the last hackathon in New York, Aurélien and some other people made an amazing documentation work to describe any metrics and what the implication and how you should use it. I don't have a lot of expertise on the metrics story, but some people have more and a lot of expertise. But the idea is that it's one line to compute, so let's do it. And then very quickly, but we have a curation layer that Aurélien will explain in detail this afternoon. Je ne sais pas combien de temps j'ai encore, mais no, it's okay for the timing. Yeah. Okay, right. So we have a curation with some tools. One tool, for instance, is to remove duplicated units because in all the kilosort version, sometimes you have 2 times the same units. So you want to remove this. You have some kind of machinery to do this. You can use this, but also some things that many people and many labs do is to put some thresholds on quality metrics. That it's for a given study, you give some quality limits you don't want you need to reach. For instance, here it's the ISI violation threshold, the amplitude cutoff. So you put some limits. And because it's a data frame, you can easily make some kind of query like this. No, j'ai pas réussi. You can make a query, which is a simple string that describes your threshold. And here you have a and. So it's a Boolean, I want this and this. And with the data frame story in SpikeInterface, in one line, you can get another data frame. And if you get the indices, the index of this data frame, it's the unit you want to keep. And the cool stuff when you have a sorting is that we have a function to reduce the sorting to get less units. Okay. In short, we have a function which is select units, give you another sorting object, which is duration, which reduces the units number, similar to the reducing the channel number. And something even better, which is more recent, is you can apply this unit reduction on the analyzer object, which is cool because in that case, you don't have to recompute any extension, because some extensions are a bit costly to compute. Of course, for the table, we only take the matrix table filtered by this unit. For the PCA, we remove the one we don't want, etc., etc. So this is cool. We have another curated analyzer, and now it tells you same number of channels, but only 22 units. So I reduce a lot the number of units. Okay, and then at this stage, you can save your analyzer to keep it on the disk with two formats. So here I am saving the big analyzer with all the units. And here I am saving the small analyzer with selected with my curation threshold stuff. And I can use a ZAR format, which is a compressed version, or I can use a binary, which is a non-compressed version. And this is cool because you can keep stuff. And depending how much extension you have used, it will be bigger or smaller. Et voilà. And you can reload your analyzer. On top of this, you can use some tools to explore. So the first one, and I'm really proud of these tools, it's the SpikeInterface GUI. And nobody uses it, but I'm still continuing developing it. So I will make a more in detail demo, but right, I like it a lot. I will try to convince you to use it later. But the cool stuff is you have both the map representation like this. You can go spike per spike. You can check that the fitting of spikes per spike is okay. Yeah, I like it a lot. You can go on the similarity map. Ah, mais c'est ça, c'est là-bas. Ouais. Wow. With a small screen, you can click directly on similar units. Wow. It's buggy because of the bars, the zoom. It's not. Normally, it's a super cool software. Another super cool stuff, which I don't like, but Alessio and Jeremy are super proud of it. No, it's really cool stuff, is that you can plot the analyzer into the web. In short, it packs everything you need, push this to a bucket, so somewhere in the cloud. At the moment, it's free, but someone pay for it. It's the Simon Foundation. Thank you. But I don't know. As soon as the Simon Foundation keeps this stuff, you push everything. I don't make the demo. And then you have this link you can share. I could copy paste this link in the Slack. And at the same time I'm clicking on it, you could do the same. And you have more or less the same story. You select a unit, you can check the autocorrelation, the cross-program, everything. So it's quite cool. Ouais.
Once it's pushed, it's there forever, or is it like after a week of nobody using it because it's really
Normally forever, but
very now reach the story that from it. But like data
Okay, so I will try to finish quickly. So just an overview that everything we did at the beginning of SpikeInterface to compare sorter is available inside this. And so you can compare output of two sorters with this simple function, which is compare to sorter. you can plot the agreement matrix, okay, which put all the unit of one sorter and all the other unit of the sorter, which in appearance is okay, some kind of square. We are lucky. But if you zoom a bit, in that case, it's kilo sort 1 and 2. On the diagonal, you have the matching number of this. It's not working well, but you have quite high number on the upper left. But the story is if you go here in the middle or on the right down side, you see that the agreement between kilo sort and itself, one version before, is absolutely big. It's only 0.3, so it's a third of the spike that match together. Right.
If on this you have one thing that output for the sorter, and then you have just this spike time for the different things that you run, is there a way to know how to create these vector objects so you can run this comparison on the SpikeInterface? What are the minimum?
Yeah, alors, a sorting object, you need to read, in short, the spike time and the spike label. And we've wrapped every sorter which is run by SpikeInterface have it. But Alicia mentioned we are also able to read output of other tools. For instance, we can read the spike from Plexon. Or if you run by your own kilo sort, we are able to read directly the kilo sort output.
As long as you have spike time and ID, you can create a sorting and do the
Ouais. A sorting object, ouais.
Just spike time and label.
Mm.
So it's a 2D column vector. And that's it. On that, you can create a sorting and use those tools.
And of course, Alicia mentioned it. Here we compare 2 by 2. It's just a big warning that the spike sorting stuff is complicated. In short, the spike sorter developer looks good, but don't trust them. They are liars, even me and some others. And for instance, for the kilo sort story, if you compare these 3 versions and you make the graph that Alicia mentioned, which is only 2 lines of code in short, compare these 3 stuff and plot this, you get exactly the same figure of SpikeInterface on any data set. And you have the same story anytime, is that they agree on some units, the big one. 2 by 2, they agree each other, but not all of them. And many of the units don't agree. So for sure, you should remove them. So it's just illustrate what's happening. And this happened on all the data set. And here it's the same representation by the sorter view. Et voilà. At the very end, you can export this to file with 1 line of code, which is cool because very often to run file was really close to kilo sort, or it was done to read the kilo sort output. But if you use 3D clue or contain sort, maybe you also want to use file. So we have some kind of data conversion with some option to copy the traces, copy the PCA or not. And depending on what you copy, you can have more or less view in the file stuff, which can be cool. When you make your manual curation with file, you can read back the results, which give you a new sorting, but curated, and you can save it, make a new analyzer. So up to you to use the output of file. And something I like a lot, but few people use it, is you can also export a report into a folder. And I will show you the report. It's something quite simple. Alors, attends. Which export everything to a simple. Alors, attendez, c'est là. Edembo. Je sais qu'on est, on est ici. Clac. Et report. And voilà. And the report is only a simple folder with some global figures. Okay. With the amplitude, with the unit location. You have the table of the in CSV file of the metrics, and you have some kind of unit summary by figure with PNG. And if you have some kind of viewer on your just an image viewer, maybe it's the best viewer ever is to go 1 by 1 to every PNG file to check your unit 1 by 1. Maybe you don't need SpikeInterface GUI or file. Maybe this is better because you can keep it's only PNG and a CSV file. Et voilà. Merci beaucoup. Attends, il y a des questions. Ah oui, Anushka. Alors, when it said internally, I'm not expert with file, but internally file, so you export a folder. So we create some file with duplication of the data more or less. And when you open file and you do some stuff, on this folder, file is adding a new file, which label what have been removed or not. So in short, it's internally to the folder by file. And so when you reload the folder, unfortunately, you need everything which is exported before. So good practice is you export this big folder, you open file, you make the clean, you read back this folder, you save the sorting object, which is lighter, and you can remove the folder. It's a bit tedious, but it's a
Yeah, but the file itself, it will change its own file to go away. So we take it over to move like
Et voilà. Il y a d'autres questions? I don't think we have question in the. No, that's it.
Hi, and say, we've had another wonderful Edinburgh catering malfunction. So we tried to get a